Okay, good morning, everyone. Okay, we were talking about the discontinuities considered in example two. So let me briefly review what we considered in the example and then go to the next one. Okay, so in this example two, we consider three types of different discontinuities. So first of all, we say a function is continuous at certain point, say a if the function satisfies the following condition, like limit of the function f of x as x approaches the value a. If this limit exists, first of all, and the function is defined at a so that we can find the value of the function at a, and then if these two values are equal, then we say the function is continuous at a point A. And in case of A and B, we consider two functions f of x. Now in A, f of x is defined by a rational function x squared minus x minus 2 over x minus 2. And that function is not continuous at the point 2 because at that point the denominator of the function becomes 0, right? So the function is not defined at 2. Now, so the in the definition of the continuity, the value on the right hand side does not exist. But in case of a b, we can define the function at 2. The problem occurs because the right hand side value and the left hand side value are different. So the equality between two sides are not satisfied. So we have and if I look at the graph of that function, we have this. So in case of a, function a, we have a rational function which is not defined at 2. And in case of b, even though the function is defined at 2, the value of the function at 2 is different from the limited value. And but in this case, in case of a or b, as I said, if I define a new function, say f tilde, which has the value of x squared minus x minus 2 over x minus 2 for all x values except 2. And then if I assign the value 3, not 1 or not other value, but 3 at 2, then the function becomes continuous at point 2. So that means this 3 is the missing value here at the graph. So if I fill that point, which means if I assign the value 3 at 2, then the graph of the function will be continuous without any jump, without any hole, but continuous. So in that sense, the discontinuity can be fixed, and such a discontinuity will be called a removable discontinuity. That means we can, by defining a function with a proper value, we can remove such a discontinuity. Now in C, we have slight different situation. We have 1 over x squared for all non-zero value x, and then we assign value 1 at 0 so that the function is defined at all real value. So when I look at this right hand side of the definition, the function is defined at 0. Okay. The problem is this. When you look at the graph of the function, we have the one on the right, on the left. So that means as x approaches 0, the function value increases without bound. Okay. So the value of, so you may intuitively say that the value of the function at 0 will be infinity. We sometimes use that expression, but that is not the exact expression because the infinity is not a real number. right? So this infinity is a conceptual symbol, right? But anyway, some people simply say the value of the function will be infinity, meaning as your x approaches zero from the right or from the left, the values of the function increase without any bound. That means the values of the function can be as large as you want as x approaches zero. So in that case, no matter what this function has at zero, I mean, regardless of the value at zero, we cannot fix this discontinuity because the value of the function is infinite. So such a discontinuity is called infinite discontinuity, meaning one of the left-hand limit or right-hand limit of the function will become infinity as x approaches a certain value a. Okay, such a discontinuity will be called infinite discontinuity. Now, the fourth type of the function we considered in this example was this function representing the largest integer less than or equal to x. And if you draw the graph, then you will see some graph-like steps as in the graph in D. So in this case, the right-hand limit and the left-hand limit of the function at each integer value are different. So in this case as well, we cannot remove such a discontinuity, but this discontinuity cannot be removed not because the value of the function is infinity, but the right-hand limit and left-hand limit are different. Okay, so the limit of f of x as x approaches a, this value does not exist. And the left-hand limit and right-hand limit have some finite difference. So such a discontinuity is called jump discontinuity. Okay. So in case of C, the discontinuity is called infinite discontinuity because the function value increases without bound, and the discontinuities in D are called jump discontinuities because the function jumps from one value to another at a given point. Because the right hand limit and the left hand limit are different. Now, sometimes we need to consider, before we go to the next one. So let us consider the graph of D. Okay. Now, in this case, the the left endpoint of each step is filled, but the right hand limit endpoint is not filled. In other words, if you consider any x here, and then if you let this x approach 1 from the right, function value approaches the value 1, and that is the same as the function value at 1. Of course, the left hand limit is different. I mean, the limit of the function of this function as x approaches the value 1 from the right, that equals the value of this function at 1. Okay, of course, the limit of this function as x approaches 1 from the left is different from this right hand limit. Okay, so these two limits are different, so we have discontinuity. But when I just look at this, just one side of the function, if I just look at the right hand limit of the function, then that limit equals the value of the function at the point 1. So if real function satisfies such a property, then we say the function is continuous when I look at just the right hand side. And mathematically, we say the function is continuous from the right at 1 because the function satisfies this relation. The limit of the function as x approaches a or 1 from the right, the limit exists, and that is the same as the value of the function at a. So the function we considered in example 2, especially d, there is an example of a function which is continuous from the right at each number. Okay. Now, if I consider some function f, if the function satisfies this relation, so the left-hand limit of the function as x approaches a equals the value of the function at a, then we say the function is continuous from the left. And of course, if your function is continuous at a, then that will imply that this function f is continuous from the right at a, and it is also continuous from the left. Okay. So if your function is continuous at certain point, then that will imply the continuity from the right as well as the continuity from the left. If your function is continuous from the right as well as continuous from the left at one point, then that will imply that your function is continuous at a. So far we considered a continuity of a function at a one point, or one-sided continuity at one point. Now sometimes we may consider the continuity of a function over some interval. We say function is continuous on some interval if it is continuous at every point in the interval. And if f is defined only on one side of an endpoint of the interval, then we understand this continuity at an endpoint to imply the continuity from the right or continuity from the left. I mean, if people say f is continuous on some closed interval, say from a to b, then at a we imply, so this continuity at a implies the one-sided, the continuity from the left, from the right, and at b we imply the continuity from the left. That's what we mean by some continuous function on some closed interval. Sometimes we say your function is, sometimes we just say f is continuous. Then that means, okay, that means f is continuous on its domain. Okay, so as an example, we say the function f of x defined by sine x is continuous. We simply say this function is continuous. That means it is continuous at every point in the domain of the sine function. Now, what is the domain of the sine function? Every real number. So this continuity means this sine function will be continuous at every real number. Sometimes we say, some people may say tangent function is continuous. Then that means, okay, that means the tangent function is continuous at every point in the domain. Now, at every so in that case, you need to read this meaning from the context. So when people say tangent function is continuous, then that means this function is continuous at every point in the domain, which means x is not, say, pi half, or not and the integer multiple of pi plus pi half. Okay. But some people may say tangent function is not continuous. Then in that case, that person implies that person considers every real number x, including, say, pi half. Okay, so depending on the context, okay, you need to understand you need to distinguish, okay, the meaning of continuity. So that's what people usually, you know, talk. But anyway, you need to understand this meaning from the context. Now, if I have a continuous function, say, suppose that I have two functions, say f and g, and if these two functions are known to be continuous at point A, and suppose that c is any constant, then when you add or subtract one function from the other, or when you multiply those functions, or when you consider the quotient, the resulting function will be still continuous at a point A. And of course, in number 5, the denominator cannot be 0 at point A. So that this function is well defined. So if you have a continuous function, then the arithmetic operation does not alter their property. So as an example, if I consider a polynomial, and polynomial, we previously learned that this polynomial and rational function have some special property that for polynomial, so if f is a polynomial or rational function, then we learned one property of those functions. The limit of f of x as x approaches a, then that will be f of a for every a in the domain of f. So we learned this property, right? So if we want to evaluate, if we want to find the limit of the function as x approaches a, then we could just plug in the value to the function and evaluate the function there, right? Now, in our fancier expression for this property is that this function is continuous at point A. Now, if that, in case of the rational function or polynomial, so this equality means that function is continuous at every number in the domain. So, in other words, any polynomial will be continuous at every point in the domain, which is the whole real line. In case of the rational function is continuous whenever it is well defined. In other words, if you consider any point in the domain, meaning, so if your function, rational function, is defined by, say, some polynomial divided by another polynomial, then that is continuous at all the real numbers in the domain, meaning the denominator of the rational function h cannot be 0 there. So as long as the denominator is not 0, so that the rational function f can be well defined, then your rational function will be continuous. That's what we learned, right? And now I'm just rephrasing that expression. So previously we have this property. Now I'm just repeating the same statement, but with a slightly different expression. And okay, you can read this property, and the point is, so as I said, some people may say tangent function is continuous. Some people say tangent function is not continuous. Okay, now you need to understand that expression from the context. So if someone says the tangent function is continuous, then that means you are considering at every point in the domain of the tangent function. Okay, and in that case, this half pi or 3 pi half, those are excluded. But if somebody says tangent function is discontinuous, then that means they are talking about every real number. Okay, so depending on the context, you can talk about this discontinuity or continuity of the tangent function. So far we considered several functions like polynomials, rational functions, or trigonometric functions, exponential functions, or root functions. So far we considered several types of functions, like even including the logarithmic or exponential functions. So these are all continuous. Okay, so these are all continuous, including the trigonometric functions like sine, cosine, or even tangent. If if I restrict the value of x in the domain, okay, I'm not talking about every real number. I'm talking about every point in the domain of these functions. So as long as these functions are defined, like logarithmic functions are not defined at zero or negative values of x, right? So if I do not consider such case, then for all positive x, your logarithmic functions will be continuous. In case of the square root function, we never consider negative value in the calculus class. And if I just consider non-negative x values, then your square root function will be continuous. So that's what I mean by continuity of trigonometric functions or root functions or logarithmic functions. So if I consider those functions in theorem 7 at every point in their domains, then these functions will be continuous. Okay, so that's what people usually say. Okay, but as I said, if you consider at every real number, then we have a different situation. Okay, now in theorem 8, if f is continuous at b, and if the limit of gx as x approaches a equals to b, then we have this situation. So limit of f of gx will be f of b. Now, since b is the limit of gx, if I replace this b with that expression, we have this one. So here, which function is continuous? F or g? F. Okay. I'm not talking about the continuity of g function. I'm talking about the continuity of this f function. So if f is continuous, then the theorem 8 tells you that I can switch these two operations, the taking limit and taking f function. These two can be switched. That means I can consider f of gx first, and then you can let x go to a. Or I can just consider limit of gx as x approaches a, and then you can evaluate your function f at the limit point. So if this f is continuous, limit of continuous function at some, say, g of x will be the same as the value of this continuous function at the limit of the g function. So the outer function f is a continuous function. That is the assumption. Okay. So if this outer function f is continuous, then limit of this continuous f of gx will be f at the limit of gx. So that's the claim in theorem 8. I didn't mention, I do not require the continuity of g function. I need continuity of this outer function f. Then I can switch this f with the limit operation. Okay. So this theorem 8 is reasonable because if f is close to a, then gx will be very close to b. And since f is continuous at b, if gx is close to b, then f of gx will be close to f of b, right? So in other words, if g is continuous at a and f is continuous at ga, then this composite will be continuous at a. So in this theorem 9, I need two assumptions. My both functions f and g are continuous. Okay. Now g is continuous at a and f is continuous at g of a, then this composite will be also continuous. In other words, if I consider my logarithmic function, okay, this function log of x is continuous at, say, at any point in the domain of the logarithmic function, say 1, it is continuous. Then when I combine this with the, say, sine function, it will be continuous at 1 because sine function is continuous at every point. So whatever the logarithmic function of x takes at 1, the sine function will be continuous there. So this composite function will be still continuous at 1. Okay. Now we have the intermediate value theorem. So what is this? So the intermediate value theorem says, suppose that I have a continuous function f on some closed interval. So this closed is important. Closed means the two endpoints a and b are included. So my f is continuous on this interval. So as I mentioned, in case of this endpoint a, I'm talking about the continuity from the right, and at b, I'm talking about the continuity from the left. And all other points in the interval, we are implying the continuity at a point in the usual sense. So if my function is continuous on this closed interval, and if n is any number between f of a and f of b, then there will be some point c in this open interval such that f of c equals to n. Okay, so this c, so okay, let me just explain this with a graph. That might be easier. So suppose that I have a continuous function f, say, whose graph is like this on the closed interval from a from a to b. Then, if I consider any point, any value m between f of a and f of b, then the horizontal line at n, this red one, will have the intersection with the graph of the function f. So we have this intersection. Depending on the value of n, there may be more than one intersections. But this, okay, but we always have such point of intersection. If your function is not continuous, say, suppose that I have some function with some discontinuity like this, then between f of a and f of b, depending on the value of n, if you choose a certain n, this line, this horizontal line may have some intersection with the graph of the function f. But for some n, there may be no point of intersection, right? So if your function is not continuous, then this intersection is not may not be guaranteed. But if your function is continuous, then the horizontal line at n will have an intersection, or there may be multiple intersections between a and b. And this open interval means that this c is not an endpoint. You may have an intersection at the one of the endpoints, but this intermediate value theorem shows it proves the existence of such c, okay, within the interval. So there may be, so if your function has one intersection with the line n at one of the endpoints, but even in that case, there may be another point of intersection with the graph. So intermediate value theorem, if I say one more time, then is that if you have a continuous function on the closed interval between a and b, and if n is any number between f of a and f of b, then the line at n will have an intersection, okay, with the graph of the function at some interior point. So C is such a point, an interior point. Okay. So this is C, f of C equals n. That means the graph has an intersection with the horizontal line y equals to n. Okay. So this horizontal line will have an intersection or multiple intersections at C. Then how can you use this? How can we use this? So here is one example. Suppose that we want to consider this equation. So 4x cubed minus 6x squared plus 3x minus 2 equals 0. If I consider such equation, okay, and the problem is to show the existence of a solution of this equation between 1 and 2. Now, this left-hand side just defines a polynomial. So if I define f of x with this polynomial, okay, on the left-hand side, then the problem just it requires the existence of a solution between 1 and 2. So in other words, we need to show the existence of the solution between 1 and 2. I mean, now if I draw the graph of the function, there must be some intersection. Now, the if I evaluate my function f at 1, then the value is -1, which is negative. And the function value at 2 is 12, which is positive. So that means if I evaluate my function at 1, the function value is -1. And the value of the function at 2 is 12. Now I know that my function f defines a polynomial, which is continuous. That's what I know. So the graph of the function f must be connected between f of 1 and f of 2. So meaning my function must be continuous between 1 and 2. Or this may not be the true form. The graph may be oscillate. Okay, I'm not sure yet. Okay, but since the graph of the function is continuous between 1 and 2, the point is the graph of the function must go through the x-axis at some point, or there may be multiple intersections between the graph of the function f and the x-axis. Now, each intersection is a point where the value of the function is 0. So each intersection is the solution of this problem, right? And this existence is guaranteed by the intermediate value theorem, right? Because this x-axis is in other words, x-axis can be represented by this. So if we think of the intermediate value theorem with 0 for n, then the intermediate value theorem guarantees that since the function f is continuous between 1 and 2, its graph must intersect with the x-axis, which corresponds to n equals to 0. So that means this function, this equation must have at least one solution between 1 and 2. So this existence of a solution is implied, but is proved by the intermediate value theorem. So that is one usage of the intermediate value theorem. Okay. Yeah. So that's what we considered in section 5 of chapter 2. And okay, and then let's go to the next section. Oh, limits at infinity. So in this section, we will let x become arbitrarily large, positive or negative, and see what happens to y. Okay, so in general, mm, in general, we use this notation to indicate that the values of f of x approaches the value L as x becomes larger and larger. Okay, so this one means the values of f of x can be made arbitrarily close to L by requiring x to be sufficiently large. And the definition will be clear if we consider some examples of the graphs. So as x approaches infinity, so that means x just goes to the right. Okay, so in other words, as x increases, the value of the function may approach a certain value L from below or from above, or the values of the function may oscillate around L, but eventually they seem to approach the value L. In that case, we use this expression. Okay, limit of f of x as x approaches infinity is L. Sometimes instead of this notation, we may use this notation. So as an example, one example will be the 1 over x function. If we draw the graph of this function, as x approaches to the infinity, meaning as x approaches to the right, the values of the function decrease to 0, okay? And I mean, all the values are approaching the value 0. So in this case, the limit of 1 of x as x goes to infinity will be 0. Another example will be the exponential function like this. So if I consider gx, which is 1/2 to the x function, then it passes through 0 and 1 point, and as x goes to the right, I mean as x increases without any bound, the corresponding function values will decrease without any bound. So in that case, we say the limit of this gx will be 0 as x approaches infinity. So please notice that there are many ways for the graph of f to approach the line L. Okay, as I said, the graphs may approach the value L from the below, from the above, or it may oscillate. Okay, so in case of this 1 of x function or gx function, they approach the value 0 from above. Okay, but some other functions may approach this limit L in different ways. And so the graphs of the function approach the value L. That means the graphs are approaching this horizontal line as x approaches infinity. So these lines, the red lines, will be called horizontal asymptote. So previously we considered the vertical asymptote the other day. Now we have a horizontal asymptote. In a similar way, we have the following definition. Suppose that f is a function defined on some interval from negative infinity to a. That means for all x values less than a. Then we say the limit of f of x is L as x approaches negative infinity. Means the values of f of x can be made arbitrarily close to L by requiring x to be sufficiently large negative, meaning as your x, okay, decreases without bound. So I mean, as your x approaches negative infinity from, okay, then, and if the function value is approaching some specific value L, then you may use this expression. So as I considered, we considered previously the f of x defined by 1 of x. The whose graphs are defined like this. And moments ago, the limit of this 1 of x function as x approaches infinity was 0. Now, in a similar way, if I decrease the values of x without bound, in other words, if x approaches, okay, if x decreases without bound, so I mean, as x moves to the left, the values of the function increases approaching 0, and the limit will be 0. And in case of this negative infinity case, the 1 over x, okay, is approaching this horizontal asymptote from the below. But previously, when as x approaches infinity, then the graphs were decreasing, right? So anyway, that is the definition of the infinity, the limit of the function as x approaches plus infinity or negative infinity. And the line L is called a horizontal asymptote if the limit of f of x as x approaches plus infinity is L or negative infinity is L. So we have the following theorem. If R is a positive rational number, then the limit of 1 over x to the R will be 0. That can be easily proved. Now that means if the numerator is fixed as a constant value 1, and if the denominator is increasing in absolute value, in magnitude, without bound. So the numerator is fixed, constant. But if the denominator is increasing in size, in magnitude, without any bound, then the whole value will decrease, right? Decrease to 0. So if R is any rational number which is positive, then the limit of 1 over x to the R will be 0. And even when limit of 1 over x to the R as x approaches infinity is 0 because the magnitude is increasing. Even when x approaches negative infinity, the magnitude of the denominator is increasing, even though the sign of x to the R may oscillate, right? Depending on the situation, but uh, so as long as x to the R is defined for all the real numbers x, then limit of 1 over x to the R as x approaches negative infinity will be 0 by the same reasoning, because the numerator is a fixed constant while denominator is increasing without bound in magnitude. Now sometimes we want to consider the following situation, and that notation is used to indicate that the values of f of x becomes large as x becomes large. Like, so when I say large, that means it became okay, larger than any finite value. So for example, if I consider the exponential function, say e to the x, then the values of f of x are increasing without bound as x approaches infinity. So in case of this exponential function e to the x, as x approaches plus infinity, the limit of e to the x will be infinity. Of course, the limit of e to the x as x approaches negative infinity will be 0. And the x-axis, the y equals to 0 line, will be on horizontal asymptote of this exponential function. And similar situation can be defined, and in that case, those symbols may be meaningful. So, for example, if I consider, say, the say gx with say e to the negative x, then we have this opposite situation. Then in case of gx, the limit of gx as x approaches negative infinity will be infinity. Of course, as x approaches the infinity, gx will be approaching the value 0. But anyway, we have this situation. So that's what this symbol implies. And you may consider some similar situations corresponding to these symbols. So that's what we mean by these notations. So please be familiar with these notations. So in chapter 1 and chapter 2, I was this reviewing the some basic definitions of the function and the some exponential function, polynomial, rational function, and algebraic function. And we considered some basic notations. Okay, first of all, we just considered basic definitions of the limits. And then we considered some simple properties of the limit of some function or some functions. And we considered the meaning of some notations, a limit of some function or limit of a function as x approaches some specific finite value or x increases or decreases without bound. So we considered several such situations. So if you are familiar with those definitions or notations, then that is fine. But if you are not familiar with any of those, please go over these materials and then please make sure that you understand these symbols or notations. Okay. So I was just reviewing these basic definitions. So that's what we considered so far. Okay, now before we go to the chapter 3, I want to go over some meaning of the tangent. Okay. First of all, suppose that we have a curve C. Okay. And we want to find, so the suppose that we have a curve C and that is the graph of the function f. Okay, so C is the curve representing the graph of y equals f of x function, and we want to find the tangent line to C at some point at say at A. So at A, function has the value f of A, and this A and f of A will define one point on this curve C. Okay, and then we want to consider a nearby point at say x. So x and the corresponding function value f of x will define another point on the curve C, and suppose that x is not a point. So here is the graph of the situation. So I have this curve C, which is representing the graph of the function. So when x is A and f of A will define one point on this curve C. And at some other point, say x, you have another point Q. Then you can think of one line passing through these 2 points. This line is called the secant line. And in high school days, we learned that the slope of this secant line can be obtained by dividing the difference between the function values between P and Q by the difference in x values, x minus a. So if you divide f of x minus f of a by x minus a, then that will give you the slope of the secant line passing through these 2 points, P and Q. Okay, so that's what happens in figure 1 on the right, on the left. Now I want to change the values of x so that this x approaches the value a, and then I want to observe the trend of the slope of this secant line. So I want to let x approaches a. Then as x approaches a, the slope will, at this in this figure 1, will become steeper a little bit, and then this slope, so here is my x1, and then x2, and then x3. So as the value of x starts from x1, then x2, then x3. So in this way, as your x approaches the value, if your x approaches the value a, then slope of the secant line will approach. Okay, first of all, the secant lines have two intersections, right, at P and Q. Now, as x approaches a, this Q approaches the point P on C, right? This Q is approaching this point P on C, meaning the slope of the, so that these secant lines seem to approach this red line, which has only one point of intersection with the graph. Such a line is called the tangent line, meaning that is the line that touches the graph C, so that since it touches, it does not intersect. Okay, the secant line intersects with the graph at 2 points. Okay, this secant line intersects the curve C at 2 points, more than 2 points. And as x approaches a, these secant lines seem to approach this tangent line that just touches the graph C, meaning this tangent line has only one point of intersection, and the slope of the secant line seem to approach the slope of this tangent line. So in other words, in some sense, this tangent line is the limiting position of the secant line as x approaches a, or in other words, as q approaches p. So this tangent line is the limiting position of the secant line as x approaches a, or in other words, as q approaches p. So that is the situation. Okay. So the slope of the secant line will approach, so that the slope of the secant line, which we used m sub pq, approaches the slope of the tangent line L. So that is what we observed in the figure 1. So this red line was called tangent line, and now we want to define mathematically, okay, this tangent line. So tangent line to the curve at some point P is the line through P with this limit value as the slope. If okay, so tangent line will exist if this limit exists. Okay, so tangent line to the curve y equals f of x at the point P, or sometimes people simply say at A, that is the line through P with this slope m. Okay, so that means since this point, the slope is given, and we know that this tangent line goes through this point P, so the equation of the tangent line, so the equation y minus f of A equals to m times x minus A. So that will be the equation of the tangent line. So this equation can be well defined as long as this limit exists. So as an example, suppose that we have a parabola y equals x of x squared, which has the graph like this. And if I consider the point 1, and we want to find the tangent line, so probably we are looking for the equation of this red line that touches the graph of this x squared of the parabola at 1. So the point of intersection will be the point P with coordinate of 1 and 1. So we want to find the limit of the slope of the secant line. So the slope of the secant line is obtained by this f of x minus f of 1 over x minus 1. And then you let x approach the value 1. So here f of x is x squared. So x squared minus 1 over x minus 1 as x approaches 1. We want looking for that value. Now, if I factor this x squared minus 1, you can rewrite this x squared minus 1 as the product of x minus 1 times x plus 1. Now note that as now in this limit, we are x approaches the value 1, but approaches that does not reach the destination 1. Okay, so x approaches the value 1, but we do not consider the case when x equals 1. So that means x minus 1 is not 0 when I consider the limit of this expression. Since x minus 1 is not 0, I can remove that term from both the numerator and denominator. I can cancel that term. Then what remains will be just x plus 1. X plus 1 is a polynomial. I can find the limit of this polynomial by evaluating this polynomial at 1. So if I plug in that value, you get the value 2. Now, please remember, in the previous example, in the previous slide, when I just considered this x squared minus 1 over x minus 1, that is a rational function. But I could not directly plug in the value 1 to this rational function because the 1 is not in the domain of the rational function, because when I consider that point 1, the denominator x minus 1 hits the 0, so that the rational function is not defined. So at that point, I could not plug in the value 1 because 1 was not in the domain of the rational function. But after I cancel this x minus 1 from the numerator and denominator, now I obtain a polynomial which is continuous at every point in real line. So I can plug in this value 1 and get the value 2. Anyway, that 2 is the slope of the tangent line. So since I know that this point goes through 1 and 1, the equation of the tangent line will be y minus f of 1, which is 1, equals to slope m times x minus 1. So we get y equals to x minus 1. That will be the tangent line at 1 and 1. Or sometimes you may just have the value of the x only. So we sometimes refer to the slope of the tangent line to a curve at a point as the slope of the curve at the point. So if I go back to the previous example, we were considering the graph of this parabola. Okay, so this at 1, so this parabola f of x defined by x squared, okay, this 2, we sometimes say that is the slope of this function at this point p at 1 and 1, or sometimes we just say when x is 1. Okay, so that's what we sometimes say in math. Now, in the previous note, the m sub pq, the slope of this secant line pq was initially defined by f of x minus f of a over x minus a. Now, if I introduce h to imply x minus a, then when I move this a to the left hand side, then x will be a plus h. So if I plug in a plus h in place of x, so if I replace this x with a plus h, and then x minus a in the denominator will be just h. So this is your h, and x is just a plus h. So if I replace this, then the slope of the secant line can be replaced by f of a plus h minus f of a over h. Okay, so sometimes people use this expression f of a plus h minus f of a over h, or sometimes people may use f of x minus f of a over x minus a. So either should be fine with you. So the point is that the slope of the tangent line can be written as the limit of f of x minus f of a over x minus a, and in that case x is a variable and you let x approaches the value a. But in this new notation, f of a plus h minus f of a over h, so f of a plus h minus f of a over h, in that case h is a variable. We don't have x. So in that case, we will let the difference, when as x approaches a, the difference between a and x will decrease to 0. So in that case, we will use this expression as h goes to 0. If this function has the limit, then that limit will define the value representing the slope of the tangent line. So we can define m in two different ways, and whatever is convenient can be used. So as I said, m can be defined in this way because in that case, as x approaches a, h goes to 0. So previously, we considered this expression f of a plus h minus f of a over h. And as h goes to 0, and that was representing the slope of the, so this was representing the slope of the tangent line. So that's what this expression means in the graph. Okay, but so this expression f a plus h minus f of a, that measures the difference in function values. Okay, function values, and h is the difference in 2 points in the domain, right? You are evaluating your function at a and a plus h, right? And this h represents the difference between those 2 points in the domain x, right? So in actually in many fields of science, we consider this difference and then we let h go to 0, and then if that limit exists, then we use this symbol to describe that value, and in our class that value will be called the derivative of a function at f at point A. Okay. So that is the graphically representing the slope of the tangent line, but now we have a different name in math. Okay, in our calculus class, so this derivative of a function, so this limit, if that limit exists, then we will call that limit as the derivative of a function f at point A. And instead of this notation, we may use this, the limit of this expression, to represent the same value. And of course, in that case, you will let x go to 0, x go to a. And if that limit exists, then that limit will be called the derivative of f at a. So the derivative of f at a graphically implies the slope of the tangent line of the function f at the point A. So sometimes we use the terminology of the derivative of a function at A, but if we sometimes call the value as the slope of the tangent line at a point A. Okay, so I'm just considering two different names. Okay, so sometimes I call this limited value as the slope of the tangent line. Sometimes I call that value by the derivative of a function at some point. Okay, so please be familiar with both approach. Sometimes we use the name derivative, but sometimes if we draw the graph, then in that case, the slope of the tangent line will be preferred. Since I don't have much time for the first part, so let me consider this example after the break. Okay, so let us take a 15-minute break, and then let me resume after the break. And when you log in, please use the other link. Okay, so please click 3.16.2 for the second class. Okay, so see you in 15 minutes.